Hey guys, welcome to our first set of video notes that we'll be start utilizing this year. We've been studying dynamics, and right now we've been up until now we've been talking about things on a flat level surface, and we know that a ball sitting on a flat level surface will not roll because the forces on it are balanced, which has a net force of 0. And so what we know is that the Fg, or the force of gravity, right, we know that is mg, that's pointing down. It will have its opposing force, its normal force, and they're equal to 0. So if I utilize Newton's second law, right, F net in the y is equal to may, because they're balanced at 0, there's no acceleration in the y-axis, so it's Fn minus Fg equals 0. So we know that these guys are equal, and we've been using this little rule for a while now, right? However, when things are on an inclined plane, the thing rolls down the plane. So once again, we have the Fg, it pointed downward like this. And then we have some kind of net force that will be pointed down the ramp. Because this net force is pointing down the ramp, that acceleration has to follow. So now, since it's on the inclined plane, that net force is a result of its weight pushing down the ramp, and we'll talk about that a little bit more, okay? So here's something that is going to be, our brains aren't going to like this much, right? We have the weight. It is Fg pointing straight down. And if we remember something about the normal force, remember the normal force was always perpendicular to the surface. So in this case, the surface is at an angle. So now my normal force is pointing off at an angle here. The normal force does not always point straight up. The normal force is always perpendicular to the surface. And we're going to have this rule. It's going to be one of those conceptual things that we'll talk about. The force of gravity is always going to be greater than the normal force on an incline. And that's going to be really important to us, right? Okay. So, the first thing we have to do for inclined plane questions is we have to resolve the object's weight, right? This is the weight of the object right here, into two components. We're going to call it the Fg perpendicular and the Fg parallel. And so here's how it's going to look. So the first thing I'm going to do is I'm going to make a big dot here, and I'm going to have this arrow here represents the object's weight, the Fg. This red arrow here is going to be the normal force pointing perpendicular to the surface. If it's on an inclined plane, we're going to have this angle down here that's going to be theta. And so now for parallel, everything is going to be either parallel to the surface of the ramp or perpendicular to the surface of the ramp. So the first thing I'm going to do, this blue thing, I'm going to have this arrow right here pointing down the ramp. This is going to be the Fg parallel, or the parallel component of the weight. Then I'm going to have this arrow here. It's going to be pointing this way. It is perpendicular to the ramp. It'll be Fg perpendicular. And notice the way we set this up is this angle right here is the angle of the ramp. And so there's a similar triangles thing that we're going to use here. The trig would tell us that the Fg parallel is FG sine theta, and the perpendicular part is FG cosine theta. So that is how the trig functions work with how the weight components are set up. We also have something kind of weird, but it's going to be really useful to us. Down the ramp is going to be negative x. Up the ramp will be positive x. Up off of the ramp is a positive y, and then down on the ramp is a negative y. So this is how we're going to set up our problems when we use our free body diagrams. The problems change whether or not it's being pushed up or down using friction and all that, so we'll have to analyze the problem and make sure we understand what's going on there. So there's two important things to notice on this. Only the parallel component of FG, or the weight, and we're going to call that the FG parallel, pulls down the ramp. So it's actually the gravitational pull is directing it down the ramp. That's something kind of interesting. We'll do a couple of demos here. The perpendicular component of FG, we call that FG perpendicular, is equal and opposite to Fn. So in other words, the normal force is the perpendicular component of that. We can even use the mg cosine theta to make sure we understand that. But we'll take that apart when we do a couple of examples here. Okay, so the first example we're going to use is we have an 8 kilogram frictionless incline, 8 kilogram block on a frictionless inclined plane shown 35-degree angles, and we're gonna figure out what the acceleration is. So once again, when we set this up, negative x is down the ramp, positive x is up the ramp. So the first thing we do is we're gonna have a big dot here. So we're kind of zooming in, and we're looking at this and saying, okay, there is the FG, there's the weight of the object. The normal force is up at an angle. This blue one is going to be that parallel to the ramp, FG parallel. This is going to point down this way. This is going to be the FG perpendicular. The angle involved here, there's the theta, in this case, that 35-degree angle. Okay, and so we have to figure out what the acceleration is in the x direction. So let's go ahead and start utilizing our second law. So we have sigma fx, or sum of f in the x direction, is mass times acceleration in the x direction. Okay, so if I'm looking at this, the only thing that is happening in the x direction is this blue force here, okay? So it looks like it's directed down the ramp, so it's going to be negative FG parallel. And it looks like there's no other forces in the x direction, so it's going to be mass times acceleration in the x direction. I then start breaking it down because the only thing I have here is a mass, and I know gravity, so I start breaking it down as far as I can. This is FG, and since it's the opposite of that angle, we'll use the trig sine theta equals MAX. FG is mg. Equals MAX. And then if we follow the math here, it's negative mg sine theta over m equals AX. And if you notice, the masses cancel out. Leaving me with negative g sine theta equals AX. Plug some stuff in here. So 9.8 sine of 35. So I get AX, or acceleration in the x direction, is negative 5.62 meters per second squared, or the other way to say that is 5.62 meters per second squared down the ramp. Okay, so here we only had to analyze the x direction. Let's do a quick analysis of the y direction, okay? In the y direction, it looks like I have of the Fn going up. So Fy equals MAY. For our problems, the assumption is the acceleration in the y direction is going to be 0. So that's an assumption we can always make. Looks like we'll have the normal force going up, the Fg perpendicular going down. We know that's equal to 0. So the math tells us here that it is Fg perpendicular. So Fn is equal to Fg cosine theta, because the trig told me so. And when I plug stuff in, it's mg cosine theta. So I'm plugging in all my known values. So it looks like the normal force here is 64.2 newtons. Compare that with Fg equals mg. And so when I plug that in, I get 8 times 9.8. I get about 78.4 newtons. And when I compare the Fn and Fg, the Fg is still greater than Fn, and so that is going to be important to us, right? That the normal force is now just a component of its weight. It's not the whole thing, and that'll be important for us. Okay, we have another question. Again, a frictionless ramp, so there's not going to be any friction involved for us here. And so what we do is we do the same thing. We always approach these using a free body diagram. We have the Fg pointing down. We have the normal force pointing off at an angle over here. The parallel component of weight pushing down the ramp is going to go this way. So Fg parallel. Then I have the perpendicular chunk right here. It is Fg perpendicular. And then the angle that we're looking at is this guy right here. So now what we have to look at is we have to find how much force is required to push up this thing, up the frictionless ramp at a constant velocity. So what that's telling me is there's some kind of force being directed. I'm going to call that F sub P. There's a pushing force going up the ramp. Constant velocity means the net force in the x direction should be 0 newtons. So let's apply Newton's second law in the x direction and figure out what's going on. Up the ramp is going to be positive, down the ramp is negative. So Fp, that's positive, minus Fg parallel, that's the negative chunk. There's no other forces occurring in the x direction, so this is equal to 0. So the math here tells us that the pushing force is equal to the parallel force. So let's plug everything in that we know. Fg parallel looks like it is Fg sine theta. So Fp equals mg sine theta. So let's plug in some numbers. 11 kilograms, 9.8 sine of 58. Crunch some numbers, we should get 11 times 9.8 times sine 58. We should get a 91.4-ish Newton pushing force up the ramp. Right? So if you don't put up the ramp, I want you to emphasize the positiveness or the negative, right, if it's going down the ramp. So the most important chunks of this are understanding this guy right here, the net force is 0, performing Newton's second law, that's one of these pertinent equations that we have to write, and then obviously understanding the free body diagram and putting everything in the right order. Okay. Once again, on this one, we're not going to do the total analysis, but once again, the normal force minus the FG perpendicular is going to be 0, so the normal force is still that perpendicular piece, which is still a chunk of the weight, okay? So once again, the normal force is going to be less than the gravitational force on the object. All right, cool. So we have the last question that we'll look at, and now we have a frictional force involved. So we have a block of a certain mass sitting on an inclined ramp that has a coefficient of friction. So now there's friction involved. So there's no pushing or pulling. What's going to happen is the block will try to slide down the ramp of its own accord, according to our demos here. So once again, here's our weight vector pointing straight down. And this one looks like it's set up a little differently. We flipped things around, but still functions the same way. We have the normal force going this way. The weight of the object is going to want to pull it down the ramp this way. This is the FG parallel piece. The perpendicular chunk is going to go right here, the FG perpendicular. My theta is this angle here. And in this case, we're going to have this frictional force that's going to be pointing up the ramp. And again, up the ramp is going to be positive x and negative x. So now we have to figure out what the acceleration in the x direction is. So we're going to perform analysis using Newton's second law, sigma fx equals max. And here it looks like everything going up the ramp is positive, so friction force is going up. The FG parallel is going down, equals max. So I'm going to start plugging stuff in. Friction force is mu times the normal force. FG parallel is FG sine theta equals ma in the x. And notice, all of a sudden, I don't know what my normal force is. I can break this down one more time, but normal force minus mg sine theta equals ma in the x. I still need to figure out what my normal force is, so I can jump over to the y side, or in the y directions, and the assumption we can make is there's no acceleration happening in the y direction, which means the normal force minus the perpendicular component of gravity is 0. So I know the normal force is equal to Fg cosine theta. And I can actually crunch this number and plug everything in to get 9.8 and cosine of 40. So the normal force is about 112.6 newtons. When I plug that in, I know I have mu, I now have normal force, I now have mass times gravity. What's kind of interesting is you can even do it a second way. The normal force would be mg cosine theta. This is mg sine theta. And this is max. Notice that the mass is in all terms, so you could actually cancel that stuff out. And you would get this equation, mu g cosine theta minus g sine theta. And so I kind of automatically know what the acceleration is. Either way, I can plug numbers in or use the math version. We should get an acceleration of negative 4.72 meters per second squared, or 4.72 meters per second squared down the ramp. And that is how we use an inclined plane and perform our Newton's second laws and free body diagrams on that. So once again, the most important pieces of this is knowing what's going on in these primary equations. Obviously, trying to scratch out the right answer is a good thing. And then the free body diagram is real critical to this. So if we're having trouble with these, it's probably going to start with the diagram. So please let me know if you guys have any questions. Let me know how it goes. All right, catch you later. Thanks. Bye.